In the last module, you learned about the continuous distributions, more specifically uniform distribution and then normal distribution. What was implied in those problems from last module was that the sample size is 1. For example, you saw a problem similar to picking a woman from full room people and then asking, what is the chance her age will be less than 55 or something similar to that? In all the problems you saw in the last module, if you take a look at it, we're only considering one instance. In this case, one woman or one person, whatever the case may be. But that's not how the real world works. We can look at one single instance, but typically look at more than one. So for example, if the sample size is bigger than it's multiple in the size of multiple, what kind of distribution could there be? So from last week, normal distribution, the implication was that the sample size is 1. If it's bigger than this, what kind of distributions are we going to consider? Well, again, like from last time, you remember that there are infinitely many types of distributions. But it so happens that if the sample size is bigger than a certain size, in this case, the sample size is bigger than 30, all the distributions will follow normal distribution. How do we know that? Well, there's a theorem that's called the central limit theorem. It says if the sample size is bigger than 30, no matter what the underlying distribution is to begin with, if it's distribution or sample size is 1, if the underlying distribution is, say, binomial, it really doesn't matter what it starts out with. If the sample size is bigger than 30, then everything follows normal distribution. So what that means is that as long as the sample size is bigger than 30, we don't have to consider any other distributions other than normal distribution. That's part of the reason we study normal distribution, because it's applicable in many situations, whether it's sample size of 1 or multiple. Multiple being, in this case, bigger than 30. So if we know how to do normal distribution, we know how to follow central limit theorem kind of problem. The way to identify between the two is that for the normal distribution, you knew that the problem has to stay normally distributed with the mu and then the sigma. Under central limit theorem, I don't have to say something, whatever the situation is normally distributed. I'll know it's going to be normal distribution as long as the sample size is bigger than 30. So watch out for that. You know, oh, I'm doing central limit theorem problem, which, by the way, is abbreviated CLT. Okay. So under normal distribution, we look at the mu, sigma, and then the single instance of whatever we wanted to analyze. On the CLT problem, we follow something similar to normal distribution, but not quite exactly right. Under CLT theorem, we're going to look at the average of whatever that you're looking at. Not, in this case, we're looking at the single instance. But the difference is, right now, we're looking at the average, the mean, the sample mean. So to analyze the sample mean, we have a mu, but over here, mu is designated as mu of x bar, because we're looking at the mu of the sample means. Similarly, for the sigma, we have a sigma, but sigma of x bar, because we're looking at the sigma of averages, the means. Another good thing about the central limit theorem is that it tells us that if the mu is given, it's exactly the same as the mu of x bar, so these two are equal to each other. However, the sigmas are not the same. If I give you the sigma, that doesn't necessarily translate into this. The formula derived from the central limit theorem is that the sigma of x bar is equal to sigma divided by the square root of n. So the mu's are the same, but the sigmas are different. So in a CLT problem, you see that NB greater than 30. You might see mu and then a sigma. If you see the mu, that's the same value as this, so you can just plug in whatever the number for this is into here. But if you see this in the problem, but you need this, what you have to do is use this number to calculate the mu of the x bar, or sigma of the x bar, and the formula is this. It's worth memorizing. So under CLT, we'll be analyzing the mean, and then that mean will have the mu of the means, and then sigma of the x bars, and then the sample size that should be bigger than 30. All right. So how do you do square root in Excel? The function name is sqrt, and then whatever the n is. That's how you do square root in Excel. So CLT will also have Z formula, which will now look like this. X bar, whatever that is, minus mu of x bar, whole thing divided by sigma of x bar. So this means that if you see a CLT problem, which you'll be able to identify by looking at the sample size, if sample size is bigger than 30, you're doing the CLT problem. In that problem, you have two choices. You might be given these, just simple mu, and then plain sigma. Or you might be given the mu of x bar, and then sigma of x bar. If you're given these two in the problem, great. Just plug it into the z. This z is the same as the z you saw in the, under normal distribution. So what you do is, once you find the z, norm.s.dist, whatever that z is, true. But if you're doing a CLT problem, and then you see the mu and then the sigma, for the mu's, you know that they're the same. So whatever the mu you have, use it for here, which is over here. However, if you're given the plain sigma, but you need this, so in order to get this, you use this formula to get this. So this value goes here, divided by square root of n, which you get it from the problem. That's the value you want to put down here. And I'll show you how to do all that in Excel in the next segment. Okay. So, now we're entering a new chapter. If you remember from the first module, I mentioned that statistics has two branches. One is descriptive and one's inferential. Everything we've done so far has been descriptive. But now we're going to move on to the inferential statistics. So under inferential statistics, there are a few things you're going to learn. Estimates, and then margin of errors. All right. So inferential means that we're looking at the data, and we're going to infer something and make some predictions or estimates. And under the estimates, we're going to study two things: the proportion, and then population. These are the only two things we're going to study under estimates. So under proportion, estimating proportion, or population proportion, the formula for that is, the letter for that is P, except that P is used as probability. So when we are estimating proportion, we use the p, but with the p hat. So if you see the p hat, that designates that it's population proportion. So you might have seen something like this in the paper, in the newspaper or TV, where say there's a poll. Say let's say the question was, what's your political affiliation, Democrat or Republican? So say, just making this up, Democrats, say 60%. Republicans, it's 40%. And sometimes you see here plus minus 3% or something like that. What does that mean? Well, these are conducted by surveys, so they're not always going to be perfectly, say, 60% to 40% ratio. There's going to be some marginal error. So what this plus minus means that, let's say for Democrats, the percentage could be anywhere between 57% to 63%. Because it's 60% minus 3, which is 57, or 60 plus 3, which is 63%. This range, it's called a confidence interval. I'm confident the real number, actual number, falls somewhere between these two numbers, 57 to 63%. So how do you calculate this margin of error? Well, as you might have guessed, there's a formula for that. So the margin of error is big E. So formula for the big E is Z square root of P hat Q hat over N. So if you remember, the P hat plus Q hat add up to 1. So if I give you P, say, to be 0.6, then you know the Q is going to be 0.4, which adds up to 1. Z will be given to you, at least in this class, and it's typically 1.96. So if you see it, if you are asked to calculate the E, and then that Z is not given to you, you can assume it's going to be 1.96, at least for this class. So, and I'll show you how to do this in Excel as well using an example. But right now I wanted to show you the formula. The second category of estimates you will do is population. And with the subtext, with the known sigma. So to estimate the population mean with the known sigma, what we'll use is we're going to use the sample mean to estimate the population. And similar to that, the error calculation is Z times square root of sigma over n. So that's where the formula comes from. And the confidence interval is written such as like this: x bar minus e, the population mean, and then x bar plus e. Okay. Again, that z will be given to you. Alrighty. The second category under the population mean is that the population mean without a known sigma. Okay. We say a known sigma because if you know the sigma, we can use normal distribution to figure out the error and then confidence interval. But the reality is that in the real world, it's very difficult to calculate the actual sigma. So there are cases where you do not know the population sigma. So in that case, what do? Well, we use the best substitute, which is called a student t distribution, which uses t as the variable and introduces another one, degree of freedom, also known as df. And to calculate the degrees of freedom, the formula is whatever the sample size is minus 1. So if you ever run into a problem where you're asked to estimate the population mean without the sigma, what you do is you go with the student t distribution, which uses the t as a variable and degrees of freedom, which the formula is n minus 1. So now I'm going to follow up with Excel examples.
Now you know the difference between the normal distribution problems and the central limit theorem problems. Let's take a look at both problems side by side and see where they're different. So this problem, given that the mu is 170 pounds and then sigma is 30 pounds, find the probability that the individual man is randomly selected that his weight is going to be less than 175 pounds. The weight is normally distributed. So just like before, you're going to figure out the z-score, and to do that you need the mean, the standard deviation, and then the given weight. So following this formula, I get the z-score of 0.16666. So then once I get the z-score, I plug it into the norm.s function, and I get the probability of 0.566, which is about 57%. So the probability that his weight is going to be less than 175 pounds is about 57%. So that's the usual normal distribution problem. So if you take a look at the next problem, find the probability that the 40 randomly selected men will have a mean weight that is going to be less than 175 pounds. The mu is 170 pounds and sigma is 30 pounds. So how is this different? Well, it doesn't say explicitly that it's normal distribution problem, but you know you're going to follow the normal distribution sequence because the n is greater than 40. And then given the mu is 170 pounds, sigma is 30 pounds, you know that it is a CLT problem. So the mean is 170 here, the standard deviation is 30. But for the CLT problem, you will need the standard deviation of the x bar, which is this formula right here, sigma divided by square root of n. So that means 30 divided by square root of 40. So if I do that in Excel, B22 is 30 divided by square root of 40, which is the n here. I get the standard deviation 4.74342. And then given weight is 175 pounds, so I'm going to use these numbers to calculate the z-score. So B24, which is a given weight, minus the mean, which is B21, divided by the new standard deviation, which is 4.74342. So I get the z-score about 1.05409. And I'm going to plug that into the norm.s this function, which gives me the probability of 0.85408, which, so let's say it's the probability that the average weight is going to be less than 175 pounds is at about 85% chance. Okay. Moving on to the next problem. So now we're into the inferential statistics, and like I mentioned in the lecture notes, there are two types you're going to do. One is population proportion. So, and this is a population proportion problem right here. I know this is a proportion problem because we're talking about the 70% of some randomly selected respondents. So this number 70% represents the proportion. So for this problem, I'm going to find the margin of error and a confidence interval, given that the confidence level is 95%. When you see the confidence level is 95%, you know that the z is going to be 1.96. So this p hat is 0.7, which is the 70%. If p hat is 70%, then the q hat is 30%, which is the same as 0.3. Z is 1.96, like I mentioned, and n is going to be 1,501 respondents, which comes from here. So the margin of error calculation, the formula is this thing. E is equal to z times the square root of p hat q hat over n. So following this formula in this cell right here, B8 is 1.96. SQRT, that's how you do square root. B7, B8, or B6, B7 divided by B9, which is n. So if you punch that in, you get 0.023, which is about 2.32%. So the margin of error is about 2.3%. The confidence level is 1.96, so then the confidence interval is given by subtracting the p hat minus the margin of error, and then p hat plus the margin of error. So it's a minus here, and it's a plus here to get the interval. So the proportion, the interval is somewhere between 0.677 and then 0.723. Okay. So now, moving on to the next set of problem. This is going to be a proportion mean problem with the known sigma. I know this is a mean weight problem because it says so. And I know that sigma because it's given to me here, 30 pounds. So I'll use these two numbers to figure out the margin of error and the confidence interval. Again, the confidence level 95%, so that means that z is going to be 1.96. As a digression, if the confidence level is 90%, you can use a z of 1.645. Or if the confidence level is 99%, you use a z of 2.58. But for this problem, let's use 1.96. So the x bar is going to be 175.55. The standard deviation is 30. N is 50. And the z is 1.96. The formula for margin of error in the mean problem is that the E is z times sigma divided by square root of n. So using that formula in this cell, B10 is 1.96 times B8, which is a standard deviation, divided by the square root of B9, which is here. Punch that in, you get 8.3, say. So the margin of error is about 8.3 pounds. So to calculate the confidence interval, same thing, x bar minus the margin of error, or x bar plus the margin of error. So minus here, plus there. So the interval is somewhere between 167.25 and then 183.85. They don't quite match because I did this in a calculator, but for your answers, you can use these two numbers. Okay. Sometimes you're asked to calculate the necessary sample size given some information. So suppose the confidence level is 95% and we want to calculate the necessary sample size for sigma of 15. Let's assume that you're given the E to be 5. What is the necessary sample size n? The formula for that is this thing here. Z times sigma divided by E, whole thing squared. So I'm going to do this calculation, 1.96 times 15 divided by 5, and then square that number. So 1.96, standard deviation is 15, error is 5, n is then b6 times b7, these two numbers, divided by b8, whole thing in the parentheses, and I'm going to square that. So you get 34.57. So do you go down or do you round up? Well, typically you want to be cautious. You want to have a bigger sample size than smaller one. So we're going to err on the side of bigger size. So you always want to round up. So if you get 34.57, you round it up to 35. So we'll say that the sample size of about 35 is needed for this problem. Lastly, sometimes in the real world, you do not know the population standard deviation. In that case, you typically have to calculate your own standard deviation, which will be the sample standard deviation, which is here. If that's the case, we cannot use normal distribution. We have to use what we call the student t-distribution. And if you ever run into this problem, this is how you do t-distribution problem. One of the things you need to know is t-distribution requires what's called the degrees of freedom, abbreviated df, and that's just n minus 1, meaning that in this case 50 minus 1, and you follow the directions here to solve t-distribution problems. So that's how you do estimation in this module.